Hello, everyone. Thanks a lot for coming. Thanks a lot for the introduction. Let me also thank the organizers for putting together this wonderful program and also this very nice week for this conference. And yeah, I'm going to tell you about some work in collaboration with Irene at CERN. That is about some tensionless string limits for the conformal manifolds. You will understand what I mean during the talk. So let me start with some broad motivation. This is something this will have to do about the distance conjecture, so let me introduce it quite quickly. And let me also go to the fun. So the distance conjecture, we know, is about the moduli space of the theory, which is parameterized by exactly massless scalars. And it tells us that whenever I go to one of these infinite distance points, I will always find a tower of states that is becoming exponentially massless, as this in Planck units. And in particular, let me remark this parameter alpha here that I'm going to call the distance parameter, and it's going to be the main protagonist of the day, so please keep it in mind. We know this conjecture, we have a lot of evidence for it, lot of top-down evidence, both from string theory, it's insane the amount of evidence here, I cannot put everyone, I'm sorry, I apologize, and also in ESI CFT. Not only that, we have some bottom-up motivations, and we also have some connections to other conjectures, we have phenomenological implications, ... This is just to point out that it's a very interesting conjecture we know a lot. And of course, I will not talk about all of this. I will focus in this ESI CFT part of the story. So the first thing that I need to explain to you is how the distance conjecture looks in ESI CFT, which is the question that was asked in these two papers. So for that, let me start with some ESI CFT basics. If I have a field in ADS with mass m, it's going to be dual to a primary operator, not necessarily primary, sorry, an operator of conformal dimension delta. And out of this dictionary, you can read off that what I was calling the moduli space in the ADS is going to get mapped to the conformal manifold. What is the conformal manifold? The conformal manifold is parameterized by what we call exactly marginal couplings. What that means is that I have a CFT with some coupling that I can tune to any value, and the CFT will remain conformal. This is something very non-trivial. We are very used to that any theory we work with, you deform it with some coupling, now it interacts, now it's not conformal. But still, you can achieve this, in particular if you put supersymmetry. In fact, you can be more precise, and you can see that also the moduli space metric that you can read off from the kinetic tensor of the scalar gets mapped to the natural metric in this conformal manifold, which is the samologic of metric that you obtain by taking 2-point functions of these marginal operators that are dual to the scalars. So you have a very well-defined setup, you understand what you're doing. Also from this, now you say, okay, what will be the distance conjecture? Well, the distance conjecture then gets mapped to the statement that at infinite distance, there should be a tower, an infinite tower of operators, whose conformal dimension is going to the unitarity bound exponentially with the distance. And that's it. Then the next question you can ask is what kind of operators? In particular, because this unitarity bound depends, for instance, on the spin of the operator. Now you take CFTs, you take as much as you knew, you compute it, and what you find is that you always find higher spin operators. So what you seem to find is that this tower always has something to do with higher spin operators. And all of this is very nicely encoded in this CFT distance conjecture that was put out by these authors. Let me not enter really into the details of the conjecture. The main point that I want to make, and this is why I'm writing this here, is that this is a very precise conjecture with very, very precise assumptions. I'm assuming a conformal manifold of a local CFT in more than 2 dimensions. It has very precise parts with very, very precise statements. And maybe even more importantly, it is in a very well-defined framework. It's the framework of conformal field theories. Why is this important? Because when I gather all these conditions, I can dream of going to this framework and prove it, and stop having a conjecture and have a theory. And it seems that this could actually be possible because, in fact, the first part has been already proven in this paper. And when I say proven, I want to remark that I don't put any other assumption. We are really assuming conformal manifold, local CFT, more than 2 dimensions. In particular, we are not assuming supersymmetry. This is just valid whenever you have a conformal manifold. No, the equals to is just like an outlier. I will give a couple of comments about it. Well, one comment that is now. And let me also point out that the existence of the stress tensor, which is the local statement here, local CFT, is completely irrelevant. And this is important because in the bulk, this means that I have dynamical gravity. Now, let me also point out that, moreover, the analogous statement in the 2D CFT, which is like the same statement, just get rid of the higher spin, and now talk about scalars. The analogous statement that when the cap closes, this is at infinite distance, has been also proven with similar techniques in this paper by Aure and Wang. So with this, what I want to say is that it seems that it's really possible to, in the future, to have a CFT distance theorem, which I think will be something very remarkable. Yes. Higher spin, sorry. Yes, I was taking this. Yes. However, I won't follow more in this direction for this talk. What I'm going to do is to come back to the bulk and ask about the stringy origin of these higher spin states. So we are finding that at infinite distance, you always find higher spin states. So then I can think in string theory, what are these higher spin states? How are they appearing? What am I getting? So in order to do that, let me start taking some inspiration from the emergent string conjecture. The emergent string conjecture tells us that as you go to infinite distance, the leading tower is going to be either KK or excitations of a weakly coupled string. And then there is a very easy way of distinguishing these two towers, and it's that the KK tower has no higher spin fields. It has a spin 2, but I'm talking about higher spin 3 and more in particular, while the string tower generically has higher spin fields. So then the expectation is very easy. It's that these higher spin points in the conformal manifold correspond to tensionless strings, are becoming tensionless, and all the higher spin modes are becoming massless. But however, this raises a bit of a problem, and is that I'm not doing string theory in flat space. I'm doing string theory in ADS. So whenever I have a string that is becoming tensionless, the tension is going well below the ADS scale, which means that I have a string in a highly curved background, which is very hard to study. It's just very hard to go quantize this string, the spectrum, it's just hard. So what I'm going to do, instead of trying to do this, even though there are some progress in this direction, I'm going to rely on CFT results. I will come back to the CFT, I will try to compute things in the CFT, and see what kind of clues we get for the bulk. You mean like Vasiliev type drive? Yes. I'm thinking about string theories. They have the Hagedorn behavior. For instance, Vasiliev theory, they don't have a Hagedorn behavior of the higher spins. And as I will show, actually, these theories do have Hagedorn. Yes. Mm-hmm. The reason is simple. In order to get to ADS, I have to put some fluxes, and that might stabilize the radions. So it's literally what is happening. Good. So yeah, I'm going to rely on CFT results, where I can compute things reliably, and then see what I learn from about the bulk. And in particular, I'm going to take like a kind of distance conjecture approach, and is that in flat space, we have been recently learning something quite remarkable, and is that it seems that the value of alpha, this distance parameter, is telling us about the nature of the tower. So in particular, for the experts, if I write down these two equations, you will come rapidly to me and say, this is the compactification of an extra dimension, this is emergent string limit, which is what we are learning. Let me, however, mention a caveat, and is that in this paper, they find that if you decompactify to a running solution, not a vacuum, this value might change. But still, there is some notion of how alpha is telling you about the nature of the tower. So then let me apply this kind of logic to the CFTs. In order to do that, I will not be able to be totally model independent. I will have to take models in which I can compute things. And in particular, I'm going to restrict to a zoo of 4D superconformal field theories that have simple gauge group. So that means these are Lagrangian, and admit large n, and I am putting the large n because I want them to have a chance of being holographic. Okay? These theories are classified, so you can compute the alpha for all of them, is what's done in this paper. And what you find is that you have these three values. Okay, let me point out that this is quite remarkable from the point of view of the CFT, because you have like 21 theories, and when you compute something, you only get three values, so there seems to be some kind of universality class thing going on here. But let me also point out that from the point of view of the ADS, and in particular following this logic, I get something even more remarkable, because I don't have one, I have three. So this suggests that I have three different strings in ADS. So this seems to be the suggestion. Let me, however, point out that already at this level, you find that something is not working quite well, because I'm not finding 1 over the square root of 3. I'm doing CFT4, which is ADS 5, so the emergent string limit should be 1 over the square root of 3. I'm not finding that here. So that's confusing. You can go and match actually this equation, and then you find that actually these three values match the compactification to 8, 9, and 11 dimensions, which is non-trivial that it happens. So what's going on? You essentially get very confused at this point. Something that could be going on is that this intuition that I'm using is wrong, essentially. But let me, however, not give up so easily, since we are confused. Sorry. Since we are confused, let me rather take a step back and look again at this list. And in this list, there is something that you can see, and is that this particular value appears in n equals 4 super jam mills. And that one is nice because we already know the dual. We know that n equals 4 super jam mill is dual to type 2b on ADS 5 process 5, so I can already see that this 1 over square root of 2 should match the type 2b string in this setup. So the idea is to understand this case. Why am I getting 1 over square root of 2 and not 1 over square root of 3? So this is what we are going to do next. CFT. The bulk, I cannot trust it. So the thing is that whenever I talk about 4D gauge theory, superconformal field theories with simple gauge group, I can classify them. There is a classification. It's pure gauge theory. I can tell you more about the classification later. There are 21 theories with conformal manifold. There are papers classifying them. You can do it. Yes, with simple gauge group. Yeah, once I start putting more semi-simple gauge group, the list is way longer. We are trying to understand the easiest one right now. Yes. Yeah, I will show that formula in a while. It's a simple formula, it's not difficult. Yes. Yeah, this is all. Actually, what I'm doing is taking n finite and computing alpha and then taking n to infinity. So yeah, this is all super under control. This is very well-known theories. They are not difficult. So yeah, the goal is then to understand this case. And in order to do that, let me first start from the bulk, ADS 5 crosses 5. I take type 2b, I put it on the sphere. I get this kind of 5D effective field theory, plus other things that I'm not bothering to describe, where let me just point out that this is controlling the string coupling, and this is controlling the radius of the phi sphere. Now I can go there, I can compute the mass scale of the towers. There are 2 of them, KK towers, I can do this computation, string towers, I can do the computation. And now what I'm going to do is to take these values here, put them in a vector, and plot them in this. Why? Because then you know that the distance conjecture being true is the statement of the convex hull of these points containing the ball of radius, some radius. And in particular, if you choose the radius proposed by the sharpened distance conjecture, what you find here is that it is cutting, so it seems to be violated. What is going on? But this is even worse, because I didn't say anything about this potential, but this potential is stabilizing the radion, so actually only the string coupling is a modulus, so I should fix this, and then I get 1 over 2 square root of 2 in this direction, which is not the 1 over square root of 2 that I was reporting before, so I'm not matching the CFT. What is going on here? Well, what is going on, I already said, is that this is in particular the region in which the tension of the string goes to 0 in ADS units, so this is precisely the region in which my supergravity is not trustable. I should not trust these computations. I should do it in the CFT. This was the whole point of going to the CFT. So what we are going to do now is to go to the CFT. I take n equals 4 super jam mills. I can again compute the prediction for the KK towers. I can compute again the prediction for the string towers. And let me just point out that here I have been to put some supergravity input. And it's the problem that I don't know how to compute this relation here, how n is growing exponentially with some distance, because I don't have a good notion of distance in that direction. Let me, however, point out that there are progress in this direction here. And for more generalized notions, you have also all these papers. So it's an ongoing work. Now, once I do it, I have the vectors. Now I can go and plot them. And let me do it in comparison. Remember, this is what we got before. This is the region in which I can trust my theory. This is the region in which I cannot. So now I'm going to superimpose here the CFT, and the CFT does this. So you see, very remarkable. What you find is a very natural extrapolation of this line, so that, well, first of all, you see that the convex hull for the ADS and the CFT are gluing nicely together, which is not obvious. And for the convex hull connoisseurs, let me say that actually what is going on is that this point is sliding here. This is like a sliding for the string tower. And not only that, at the end of the day, what you are really finding is that the ADS and the CFT seems to join forces very strongly in order to protect the sharpened distance conjecture, which I think is something very non-trivial, because from the point of view of the bulk, this conjecture was totally out of the window. Yes. I'm going to play that in a second. Yeah, thank you. Yeah. But first, let me take a detour. Because there is a fun exercise that you can do here. And is that at some point I was writing this equation. If you dualize to the bulk, what you get is that the Kaluza line are always of the scale of the radius of ADS. This is nothing but no-scale separation from the CFT. It's how you see no-scale separation in the CFT. So let me do something fun. Let me just generalize that. Let me allow for some kind of scale separation and see what happens. And that means that for the BPS, I'm going to write down this. For those of you that like more the bulk, this is like a weird stabilization of the S5, something that I don't find in type 2B on an S5. And this is like a weird BPS spectrum. It's a BPS spectrum that is not the one on equal 4 super mix. I'm playing this game. Why am I playing it? Because then I can compute everything again. And if I have anti-separation of scales, I find this, in which you see first that the convex hull of the ADS and the CFT are no longer gluing together nicely. They are not glued together. And second, I'm finding a violation of the sharpened distance conjecture here in the CFT. Now I can take also the case of separation of scales. I find now this plot, and I exactly reproduce the same. They don't glue together, and I find again violation of the distance conjecture, in this case in the ADS. Let me, however, make a little caveat, and it's that this region here is in particular the region in which the tension of the string is below the sphere, but above the ADS. So one could say whether this is trustable or not. I think it is because in particular these modes don't see the sphere. They don't have KK momentum on the sphere. But this is a bit tricky. All in all, what I wanted to show with this detour is that there seems to be some nice link between the sharpened distance conjecture and no separation of scales, which is something to be explored. Yes? In particular, this is going to work for all the theories that have alpha 1 over square root of 2. And not only simple gauge factor. Even if I have any number of simple gauge factors, if I find a direction in which I have the 1 over square root of 2, which I can, then this will reproduce exactly. Now, further than that, I'm not sure. It's a bit tricky to know what are the actual assumptions that I'm doing. Okay, so let me recap, and in particular, let me now say why I was not getting the 1 over square root of 2. So there are two reasons. The first reason is very simple. Is that what we call emergent string limit in flat space is a limit in which the string scale goes to 0, but also some Kaluza line are going to 0. And the limit that I'm finding is a limit in which the string scale is going to 0, but the Kaluza line is staying quiet. So in particular, what is going on is that typically if I do this plot, this is the usual emergent string limit, and indeed I find a 1 over square root of 3. Everything is matching what we know. But this is the conformal manifold. Oops, yes. So essentially what I'm doing is finding a projection. But before I was saying that if I project this, I get the 1 over 2 square root of 2, right, instead of the other. There is another reason why this is changing. Again, the string is in a highly curved background. I have to take that into account. And what this is doing is that this is changing the quantization of the string. How is this happening? Well, actually, in this case, I can be more refined, and I can say what is going wrong in the computation of alpha. So when I compute alpha, typically I put two inputs. One of them is the moduli spec metric for GS, which you can just check in the ADS, it works. It's okay. This is not the problem. And the other one is how the mass of the string excitation behave with GS. And this is what is going wrong. In the flat space approximation, you have the typical MS going at square root of the tension, which gives you this power of GS. But if I go to the CFT and I ask the CFT, how is this behaving? I will find a GS to the 1/2. It's changing. It's different. And in particular, now I can write this in this way, in order to find that the CFT is predicting that there is a subsector of the quantization of the string whose mass behaves linearly with the tension and with the radius of the ADS, which is something that won't happen in flat space. This has to do with the string seeing the ADS. Then, of course, the question is whether this is universal, or this is something only about ADS 5 cross S5 n equals 4 super mills. This is just some food for thought. The argument that I can give is the same one that I did before. These are guys that are becoming massless, so they cannot have KK momentum. So I have the feeling that they cannot see the sphere. They only care about the ADS5. And then the ADS5 is the ADS5 for any string. So it should not depend on the internal directions. But I don't have better arguments. This is just some food for thought for the moment. Yes. Sorry? No. The KK scale in the conformal manifold is totally fixed. Totally fixed, completely fixed. Anything I do with the string is going to decouple. Yes. The only limit in which I see the string coming down with the KK is this critical, is this limit here. The only one, which correspond a way to large N limit fixing the top coupling in N equals 4. So it's also a special limit for the CFT. Does that reply your question? It's less than the KK. Yeah, generically. And that will happen not only in this example, for all the CFTs, all of them, anyone that I can think of. Okay, so I have no idea how am I doing with time, to be honest. 10 more minutes, okay. So then, okay, this was nice. I was able to reproduce this value from the type 2B. We understood this one, that's great. But what about the others? I was saying at the beginning that my reasoning seems to tell you that these are two new strings in EDS, but maybe one could say maybe this is not the case. Maybe it's the same string just in a weirder background. So let's try to reply this question, but now we find a problem, is that if I take a CFT for which I don't know the string realization, you are asking me to detect a string from the CFT, which is a very, very, very hard problem. So since I cannot do that, what I'm going to do is to look for physical properties of the CFT that will only depend on alpha, because then it seems that there is some physical thing that is universal with respect to alpha. So I'm really classifying the CFTs as universality classes. And in particular, I'm going to discuss two of them. One of them is the ratio between the A and C central charges. I'm going to explain in a second. And the other one is the Hagedorn temperature of the theory at large N. So let's go for it. The first one is really easy. This is the equation that Irene was mentioning. You can compute alpha in general. This is just the central charge, and this is the dimension of the gauge sector that is decoupling. It's very simple computation. But now what I can do is that if I assume that what is decoupling is all the theory, I can write out the dimension of the gauge group also in terms of the central charges A and C. So I will get this equation, I invert it, and as I was promising, the ratio of A over C is a function of only alpha. But I was telling you that I will find some physical properties. So what is the physics here? Well, the thing is that we know that A and C control very relevant aspects of the effective field theory in the bulk. And in particular, most notably, we know that if A is not C at large N, then the bulk cannot be described by a weakly coupled Einstein gravity in low energies. So essentially what I'm telling you is that only the theories that have alpha 1 over square root of 2 that we already understood as the type 2B admit a low energy Einstein gravity. Or on the other hand, I'm telling you that the other two will-be strings will never reduce to an Einstein gravity in these ideas. They won't have an effective description in that sense. Yes? Sorry, can you repeat? Let me think. I think this equation I can write it down for any n, but then the value of alpha that I was giving you was this large n alpha. Yes. Then there will be subleading corrections to the large n. That will be like gravitational corrections to the alpha, essentially. Good. Very good, very good. Let me go for the second point. The second point I was telling you what has to do with Hagedorn temperatures, right? So let me introduce. Let me consider the partition function of the theory, the thermal partition function, which is, as we know, just the sum of states with the Boltzmann separation, or I can also write it down in this way if I define the density of states. Now, we know that in certain theories, you find that this is blowing up as the temperature approaches some Hagedorn temperature, and that happens only if the density of states behave exponentially, which is a very stringy signature, because essentially all the strings we know have this kind of Hagedorn behavior for the spectrum. But even more, what you find in this equation is that the very density of states is controlled by the Hagedorn temperature. All this exponential law is controlled by that parameter. So then, if it is true that I have only 3 strings that should have the same spectrum, I should have the Hagedorn temperature only depending on alpha. I should be able to compute the Hagedorn temperature for all these theories, these 21 theories, and I should find only 3 answers, only depending on alpha, which is something highly non-trivial, as I'm going to show now. So let us check it. Let me first start with 4D n equals 1 or more, SUN gauge theory. These theories are determined by 7 parameters, which is essentially the number of chiral multiplets in the representations that I can allow. You know, adjoint, fundamentals, antisymmetric, symmetric, and the complex conjugates. Now, long story short, because this is really a long story, you can compute the partition function at large n, and you can see when it diverges, and you get this Hagedorn condition. That, in order for you to understand, let me just say that this CV is just containing the information about an n equals 1 vector, nothing fancy, and this CC is determining the contribution for n equals 1 chirals. But the important point is not this equation, the important point is this parameter. I see that there is a particular combination of the parameters that is controlling the Hagedorn temperature. There is no other parameter around in this condition. So I should be able to show that this is a function of only alpha. So let's try to do it. Let me compute alpha in terms of these parameters, and you get this equation. So first, you notice that this combination appears, which is nice, but not enough, because there is another piece. So as it is right now, my expectation is not true. But we are missing something. This is something that is true for any 4D n equals 1 SUN gauge theory. But I was telling you that I want a conformal manifold. So at the very least, I should impose that the beta function for the Yang-Mills coupling should be 0 at one loop. This is something I should impose. And this is something that I can impose at large n, and I will find this equation, which is precisely relating the dangerous term to the linear combination that I like. So we are done. If I put the two things together, I will find that this linear combination is written only in terms of alpha, which is precisely what I wanted. So now this is nice and enough. You can just put it for fun, and you find this Hagedorn condition, which is confirming the expectation that we were saying, that the Hagedorn temperature only depends on alpha. But this was only SUN, so let me do the other two gauge groups. Very similar story, parameters, this control the Hagedorn temperature. If I put the distance parameter and also the beta function, I find a perfect matching, and I find that it only depends on alpha. But not only that, notice that I'm not only finding that it only depends on alpha, I'm finding precisely the same function as for SUN, which is non-trivial, because when you are doing the computations, you realize that they are not even cosines. They don't have anything to do with each other. But it happens. So we are again confirming the expectation that no matter what is the gauge group, no matter what is the matter content, the Hagedorn temperature only depends on alpha, which is what we were saying. And that will be the end of the story if it wasn't for a possible caveat, that is that many of these theories have large number of flavors as you take n to infinity, which can be a bit of a trouble, has been argued in the literature. Particularly in this paper, it was argued that it's very natural to restrict to the flavor singlet sector. It's protected by symmetry, it's consistent to do this. This is some work in progress, it's a bit complicated, but let me just show that if I take the prescription of taking the free theory, which is where I actually can compute the partition function, otherwise it's horrible, and I restrict to the free flavor group, this is the generalization of the previous result. And you see that this is what I was writing before, but with this extra piece that does not depend on anything. So again, this is still working, which is, again, very highly non-trivial because the computation for SUN and USP and SO are totally different. But everything seems to conspire such that you get what you want. So how am I doing with time? 2 minutes, so I can give the bonus track. So yeah, the bonus track is essentially that once you say that there will be new strings, you will say, okay, let's construct them in string theory. Like you want to build them. And I think I can give a possible candidate. So in particular, I'm going to talk about this type 2B on ADS5 cross S5 and an orbifold that lead to n equals 2 necklace quivers. These are, again, very well-known theories. The only thing that I want to point out is that this S5, after the orbifold, has an S1 of orbifold singularities that you blow up. So now I have some 2 cycles. I can take the B and the C field, I can integrate it, and I will get some actions. So I have some actions around. Okay, this is the point that I want to make. And then there is a very particular limit. There is a limit in which I take these actions to 0, keeping the string coupling constant. Since the only thing that I'm playing with are actions, anyone that has been doing supergravity will say this is a finite distance. There is no way that this is an infinite distance limit. However, when you check the CFT predicts that this is at infinite distance and there is a tower of higher spins, distance conjecture satisfied. So in this sense, from the point of view of the bulk, this is an infinite distance generated by quantum corrections that you were not taking into account. And then you can ask, okay, in this case, particular case, what could be the stringy origin? Well, the first thing that I can tell you is that since GS is constant, there is no way that is the F1. Because the F1 is BPS, I can compute the tension. There should not happen that as I take the limit, the tension changes. And then the only candidate that I can think of, maybe I just not being imaginative, is to take a D3 brane and wrap it in the 2 cycle of the blowout that is and that this guy you can check that is becoming tensionless. It's also BPS, so I can trust the computation of the tension. But then you are confused because this is wrapping a blow-up, so this is not propagating in ADS5 cross S5. This is only propagating in ADS5 cross S1. So this is non-critical. This is a non-critical string that typically, when you put it in flat space, does not give you rise to a tower of higher spins whatsoever. But it seems to happen when you put it in ADS. So yeah, this is essentially the candidate that we propose in this paper. I cannot say more. I don't know how to contrast the string in ADS, but it would be nice to have something else to say about this. So let me conclude because I think I'm already out of time. With this message, I think there is just a lot to learn from and about the distance conjecture in ADS CFT. In particular, in the CFT side, of course, you want to prove it. That would be amazing. And second, it will be very nice to have a distance in the n direction, in the central charge direction, because then I could be able to play this convex hull trick for the rest of models, because I will be able to compute it. In the stringy side, of course, you want to answer the question whether there are really these new strings or everything was matching just, because of something. And if you agree that there are these new strings, you want to build them. And then I will propose that these 3 brains wrapping the blowups in ADS seems like a fairly reasonable candidate. And with this, I finish. Thanks a lot for your attention.